Welcome, everybody. Welcome to the MIT Category Seminar. Today we have Conal Elliott, who's going to talk about automatic differentiation and how to do it efficiently by means of category theory. So I beg everybody who has a question, please use the chat or raise your hand or write on Zulip or YouTube. Hello, and please let's welcome our speaker, and the mic is yours.
All right, thank you very much. I'm glad to be here, and yeah, please do raise questions during the talk. I'm not going to try to cover a whole lot of material. I have some extra material at the end, but more importantly to me is that people understand. Automatic differentiation is a field that's been around for a few decades in itself, and then more recently it's acquired a lot of interest because of deep learning. At the heart of deep learning is really kind of like poor man's functional programming plus the ability to differentiate. And in the context of deep learning, we're talking about an objective function, which is usually a function from a very high dimensional input to a one-dimensional output. That's the objective function, and it's that case that has been challenging to implement correctly and efficiently. And if you look at the literature, you'll see something called reverse mode automatic differentiation, which is really targeted at this case. There's an algorithm from it's used in deep learning called backpropagation, which is an implementation of a kind of a special case of that. And it's usually presented in very complicated terms and without rigor or precision. And with a lot of a mutable state, which makes it difficult to reason about and makes it difficult to parallelize. And what I want to show today is that this kind of complexity around reverse mode automatic differentiation is really entirely unnecessary. It stems out of making two kind of fundamentally bad choices. One is to think in terms of graphs, and the other is matrices. So that these are both kind of like unquestioned choices in the field, and they're both disastrous choices. So I'm going to show if we make some different tasteful choices, that efficient automatic differentiation falls out extremely simply. We get a simpler algorithm. It's much more general, and it's easily proved correct. And so what I'm going to show you today is basically calculating that correct efficient algorithm. Okay. So here we go. So what is differentiation? That's the key question. We want to differentiate automatically, so we better know what differentiation is. And if you took high school calculus, you may have in the first year gotten an idea that derivative of a function is a number, like a slope of a function. And then if you move on to more advanced calculus, you find, well, no, it's not always a number. Sometimes it's a vector. And there are really two different kinds of vectors that it might be. They're usually not distinguished very clearly, but they're very importantly different. And then you get maybe a little higher in calculus, and you find out, no, sometimes it's a matrix, a Jacobian matrix. And really, if you continue, there are like higher and higher dimensional and more esoteric forms. And every one of these forms has its own chain rule. And they're all different. They all involve something loosely called multiplication. In the chain rule, but it's kind of harmful that they're all called multiplication because they're really different things, but they all do mean the same thing, and we'll find out. I'll show you what that is in just a few minutes. So what in general is differentiation? If we have a couple of vector spaces, A and B, vector spaces over the same scalar field, a little more than vector spaces, they need to be normed and they need to have limits. So those are called Banach spaces. Then differentiation, the script D here, it's a higher order function. It takes in a function from A to B and it gives back a function. And that's going to be from A to derivatives. And what is a derivative? A derivative is a linear map. So it's not a number or a vector or covector or a matrix or some higher dimensional beastie. It's a linear map. And all of those other things represent linear maps. That's what they're for. And so we have we can differentiate a function, and what does it give us? It gives us like a local linear approximation. It shows how the function is changing linearly at around a point A in its domain. So more precisely, f of A plus the derivative of f at A. Okay, that's the linear map evaluated at epsilon. So that's a tiny input delta. Okay, so this is a local affine approximation of f of A plus epsilon for small epsilon. And specifically, this is the property that has to hold. You evaluate f at A plus epsilon, and then you evaluate this local affine approximation. You look at the difference between them and divide by its magnitude by the magnitude of epsilon. Okay, as epsilon goes to 0, that quotient needs to go to 0. So that is a property. It's not a constructive definition. It's a property of d of f of a. Okay, and if this property is satisfiable, if there is such a d of f of a, then it's unique, and that's a theorem in the higher dimensional calculus. And I learned this topic out of a book called Calculus on Manifolds by Michael Spivak. I think it was around, the book is like 1967 or something. It's a beautiful small volume. You have good fortune to be exposed to.
I'm sorry. Shouldn't there be an exponent somewhere? Because I would feel here that the numerator and the denominator are of the same order.
Yeah. So you're asking if there should be an exponent? No, there shouldn't. But I'm intrigued with why you think there should be. So maybe we can talk about that.
No,
that may take some time to sort out. So the short answer to the question is no, there shouldn't be an exponent there. Okay. All right. So now what does it mean to automatically differentiate? And there's an obvious answer, which is that given a computable function, right? So that's what we do with computation. Whoops. Is we construct computable functions. We use programming languages to do that. And so you might think that automatic differentiation means you take a computable function and you compute its derivative. And that's an obvious definition, but it's unfortunately, it's a non-computable thing. So differentiation of computable functions is not computable. So we have to do something else, and automatic differentiation always does something else, which is that we differentiate recipes instead. So rather than just having an arbitrary computable function, and all you could do is you could sample it on its inputs, we're going to need to have, because of the non-computability, we're going to need to have some sort of recipe instead. Okay, and so what I've tried to say here, so the semantic brackets here, this means like if P is a program, okay, so there's some kind of like syntactic or quasi-syntactic representation. So, and what I mean is it's examinable, it's inspectable, that's a good way to put it. Okay, then there's some other operation, d bar, that's going to work on these recipes. So you give it a recipe P, it gives you a recipe P, and the meaning of that recipe as a function, okay, is the same as the actual mathematical derivative of the meaning of the recipe. So think of P as like some program, maybe it's a Python program or something like that. And we're saying we're going to convert Python programs to something else, maybe they're Python programs, such that the meaning of the resulting program is the derivative of the meaning of the input program. Okay, so now that raises the question of what kind of recipes should we use? And there are some very popular choices. The most popular one, I think you'll see out there in systems like TensorFlow and a bunch of other systems and in the literature, is graphs. That's kind of like almost unquestioned. And as I mentioned before, it's a disastrous choice. Choice is a generous word. It's maybe kind of a default. Another choice is imperative programs. So some popular programming language. They're still sadly imperative. So that's another choice. And the lambda calculus, that's a kind of more mathematically oriented choice of programming of recipe languages. And all of these choices work out badly. Okay, these are the popular choices, and they all work out badly. And they work out badly for a very simple reason, which is differentiation is not compositional in any nice way with respect to the vocabulary of graphs, imperative programs, or the lambda calculus. Okay, so if you take any of these three choices, you're going to get a kind of messy development. And it's going to be very difficult to prove it correct, which means it's going to be difficult for it to be correct, actually. Okay. However, there is one other choice that works out really nicely, and that's the language of categories. Okay, and why is that? It's because differentiation composes very nicely, tidally, in the language of categories. Okay, and why does composition matter? Composition is hugely important. Composition is our superpower, our human problem solver superpower, breaking down problems into simpler components and then composing solutions. It's how we're able, despite our cognitive limitations, how we're able to accomplish ambitious, forward-looking kinds of things. And so finding if you have a tricky problem to solve, finding a language in which the solution to that problem is compositional is like the most important step. Well, defining the problem clearly is the most important step. The second one is finding a vocabulary in which it's compositional. Okay. So now we're going to go back to calculus. Okay, so stop thinking about programming for a bit and go back to calculus. There's a theorem in differential calculus called the chain rule, and it looks like this. So if we have the composition of functions g and f, Okay, here I'm defining what that means. This notation is Haskell notation. I will try to explain it as I go, but if you have any questions, don't understand what something means, please do ask, because this is notation I'll be using. Okay, so sequential composition is an operation we use all the time in math and in pure functional programming. And it just takes two functions from B to C, from A to B. So this B is the common link between them, and gives you a function from A to C. And so G compose F is a function when you sample it at A. Now I'm denoting function application by juxtaposition. So when you sample the function G compose F at A, it's just F sampled at A and then G sampled at F sampled at A. Okay, so it's just the usual definition. And the chain rule is as follows. It says the derivative of a sequential composition of two functions, okay, at A, is, well, it's the derivative of G composed with the derivative of A. We got, derivative of F. So we got to sample F at A, and we got to sample G at F of A. So this is the chain rule. And you've probably seen this rule as saying multiplication here. So the derivative of G times the derivative of F. But that's actually not right. That is, you can define multiplication and redefine it for different kinds of representations. So if these things were scalar functions, you might expect to see, scalar multiplication. Or if there was some kind of vector thing going on in here, it might be a dot product or a matrix kind of multiplication going on. But they all denote composition of linear maps. So that's why we multiply derivatives. It's because the derivative means a linear map, and multiplication is defined in such a way that it means composition of those linear maps. Okay. So if you use composition instead of multiplication, then this one chain rule applies to all dimensions. Alrighty, but sequential composition isn't the only way of building up functions. There's also a notion of parallel composition. There's a couple of different, and this is the one I'm going to use. It's not really important which one you use. I'm going to call this operation fork, which is if you have a function from A to C and A to D, so same domain, different codomains, then we can kind of zip them together into a function from A to the product C cross D. Okay, and what does it do? Well, F fork G, you sample it at A, it just samples F and G both at A, and pairs up the results. Okay, and there's a nice little rule that's very much like the chain rule, which is the derivative of F fork G is the fork of the derivative of F and the derivative of G. Okay, and here they're sampled in the same place. So these are both kind of simple theorems of differential calculus, and they're like hints already that category theory is the right way to look at differentiation, because these are two of the fundamental operations from category theory, okay? And differentiation composes nicely in that vocabulary. All right, there's one more thing we need to know. Now remember I said the derivative of a function is a kind of like a local linear approximation, and the derivative is a linear map. So the kind of last important piece of information you know about differentiation is the following: that the derivative of a linear function is itself everywhere. Okay, so that's the third kind of fundamental fact we're going to use about differentiation. So this is saying that, for instance, the derivative of the identity function is linear. So the derivative of the identity function is the identity function everywhere. In other words, for all A in the domain of the identity function, the derivative of the identity function at A is id, is the identity linear map. Okay. Now you might think, okay, the derivative of the function, lambda xx, the identity function maps x to x is 1, all right? But I'm saying, no, it's really not 1. It's really the identity function. And so the reason we think it's 1 is that in one dimension, a function like function f of x equals x, when we say the derivative of f of x is 1, what we mean is 1 times. We mean the linear map that multiplies by 1. That's always what we mean when we say derivative of a scalar function is 3. It means it's 3 times. It doesn't mean 3 times. In higher dimensions, you might expect the derivative to be the identity matrix. So the matrix with like 1s on the diagonal and 0s everywhere else. Okay, but that matrix is called the identity matrix because it denotes the identity function, the identity linear map. Okay. All right, so those are the 3 things we need to know about calculus: that the derivative of the sequential composition is the sequential composition derivatives, Derivative of the parallel composition is the parallel composition of derivatives, and the derivative of every linear function is itself everywhere. Okay. Another way to say the derivative of a linear function is itself everywhere is to say that linear functions are their own perfect linear approximations, which is like obvious when you put it that way. Okay. Now, let's look at, again, the chain rule. And the chain rule is a bit non-compositional in the following sense. The derivative of G compose F is not built up merely from the derivative of G and the derivative of F, because it also needs F itself at A. Okay, so this is actually a breakdown in compositionality, and has to be addressed somewhere, or we're not going to get kind of a nice algorithm. We're not going to get an algorithm at all. And so it's very easy to fix this issue, which is we generalize differentiation a bit. We add a little bit to it, which is don't just give me the derivative, but give me the old result also. Okay, so here's an augmented function I'm going to call d hat. So d hat takes a function from A to B and gives you a function from A to B, the old result, plus the derivative at that point. Okay, so it's just a slightly augmented definition. Okay, and what's the actual definition of d hat? Well, it takes the function f, and remember this is that fork operation that kind of puts two functions in parallel and zips them together. Okay, so d hat of f is built out of f and d of f. So this is the specification. I thought I wouldn't get reminders, but I guess I do. All right, so and then we can rebuild df out of d hat f, which is just EXR is the right projection. So it takes a pair and gives you the right element of it. Okay, so we're saying that build up this pair and then throw away the second one. Now, why would we do that? It's because d hat is going to be because it's compositional. That's the one that's going to get defined kind of recursively or inductively. But in the end, we might throw away the value of the function and just keep its derivative. All right.
We have a question maybe before we go on. So somebody's asking again, why isn't the chain rule compositional?
Okay. So yeah, thank you. Yeah, you bet. Okay. So I'm using compositional in a very precise sense. Okay. And it's not compositional in that sense. So to be compositional in the strictest sense would mean that the derivative of G compose F is some operation that just uses D of G and D of F. Okay, it just combines the derivative of G and the derivative of F and needs no other information. But the chain rule does need a little bit more information. It needs something out of F itself because it has to sample D of G at F of A. Okay, so if all we knew about if all we knew on the right hand side about G and F were its derivatives, we wouldn't be able to build this composition because we couldn't sample G at F of A. Okay. So, all right. But when we if we define d hat that remembers its result as well as the derivative, okay, then we'll have f of a at hand ready when we need it. Okay. Okay. Now, this vocabulary, sequential composition, parallel composition, and particularly these three linear functions. Okay, this isn't just some arbitrary vocabulary. This is the vocabulary of Cartesian categories. Okay, so happily, differentiation itself as a mathematical operation, forget about programming or computers, differentiation itself is compositional in the language of Cartesian categories. And that's what it's that one property that makes this whole development work out nicely. That's why it works out. Okay. So as I mentioned, I'm going to be using a Haskell notation, which you may or may not have seen. If I were talking to a Haskell audience, I would be kind of explaining categories at this point, but in this slide, but since I'm talking to a categories audience, I'll point out little Haskellisms here. All right. So category is this notion. It has two operations, identity and composition, and they have their their three axioms. So this is what I'm saying here is that I'm going to be talking about some things which are morphisms from a category, okay? And they have these operations, identity and composition, okay? And I'm going to show you a few different examples of these categories, okay? And how I'm going to do it is, so this slide is defining the interface. Categories have identity and sequential composition. Cartesian categories add on three other operations, left and right projections, and this parallel composition operator. Okay, and it has its laws as well. Okay, and now, so I'm developing, so this implementation was in Haskell. And so the kind of first step to be able to give another category, well, we have one category in Haskell that we already know, which is just regular functions. But I'm going to be defining another category, which is differentiable functions, and there'll be a few others. And so the differentiable functions is exactly what I showed before. This is this kind of d hat, okay, which is a differentiable function from A to B. I'll call it a computably differentiable function from A to B. Is just a wrapper. This is just a little wrapper around a function, a computable function from A to B and its derivatives. Okay, and this is the definition. This is just the definition I gave before of d hat, except now I'm throwing in this little d wrapper. This is just a kind of, this is just a Haskellism. Okay, if we're using some other language like Agda, and I'm in the kind of process of redoing this all in Agda, we wouldn't need this extra layer of d. Okay, and so here's our specification for automatic differentiation. It is d hat is a Cartesian functor. That's the specification. Okay. So if you read the literature, especially for efficient automatic differentiation, I think you won't see any precise specification. And if you were given one, if you had to give one in terms of, say, graphs, for instance, it would be extremely complex. But in this setting, it's very simple that d hat is a Cartesian functor. Okay, so what does that mean? That it means that d hat preserves the kind of the category structure and the Cartesian structure. So d hat maps identity to identity and compositions to compositions, projections of themselves and forks to themselves. Okay, but like, what am I saying here? If you look at each of these definitions, let's take sequential composition. So I told you what d hat means. Oh, it's very important. I want to point out this is this definition of d hat is not computable because differentiation is not computable. This is going to be the specification. This is we want to solve this specification we want to, in other words, use the specification as an algebra problem, solve that algebra problem. The solution of that algebra problem is a computable function. And because it's a solution to this equation, it is a correct implementation of automatic differentiation. So this is the specification, which is non-computable. We're going to use it to derive a computable, correct implementation. Correct means it agrees with this specification. Okay. So if we look at this equation here for sequential composition, d hat of g compose f is d hat g compose d hat f. Okay, so see, on the left-hand side, this compose is on functions. We know what this composition means. This composition here is on differentiable functions. We don't know what this composition means. So, and that's true of identity also. This is identity on functions. This is identity on differentiable, computably differentiable functions. Okay, so every one of these 5 equations by itself is an equation in one unknown, which is the operation on the right-hand side. If we solve these 5 equations, we will get definitions of identity, composition, the left-right projections, and fork for computably differentiable functions. The fact that they are solutions of these 5 equations, okay, means that they are a correct implementation of automatic differentiation. Okay, so that's the game. Solve these equations for the right-hand side operations. And if you do that,
question.
Yeah.
Again, maybe David, do you want to unmute yourself directly?
Sure. So is the claim that any functor, Cartesian functor d hat of this type must be differentiation, or it has, I mean, the hatification of differentiation, or that it has to satisfy that not computable thing for the real definition of derivative?
Yeah, thank you. Thanks very much. Yeah. So it's definitely not, I'm not saying that any functor that satisfies these laws is differentiation. No, differentiation is differentiation. Okay. So d hat, what makes d hat differentiation is this specification. Okay. Now the question is, how do I come up with the implementation? And the way I'm going to do this is this. Remember I said that that because differentiation is not computable. Okay, so then we have to like give up on the most obvious thing we do, which is take an arbitrary computable function, not its recipe, but the function itself, and computably construct a derivative. Okay, so we can't do that. So instead, we're going to have to work on a recipe. Okay, the recipe that we're going to use is the idea is that we're going to go for a homomorphism. Okay, so we need to convert recipes to recipes. If the function that we're implementing, in this case differentiation, is homomorphic, okay, then the conversion of recipe to recipe is the same recipe. So the recipe you put in, we're going to use the same recipe you get out. That's what homomorphisms do. The function is homomorphic. It means you can apply that function to a recipe and you get the very same recipe, but you get a different interpretation of that recipe. Okay. So here the homomorphism is over categories, Cartesian categories. So that's why Cartesian functor is what we're looking for. Okay. So there are two things going on. We have the specification, which is d hat f, but how do we get an implementation out of that? The way we're going to get an implementation out of that is that we're going to require that we're going to find a way that d hat f is homomorphic over the language of categories. In other words, it's a functor, Cartesian functor. Okay. And then the implementation is going to be the definition of id, compose, projections, and fork. Okay. So now when you have a recipe for a computable function, translate that recipe in the language of categories. Okay, and then use the same recipe, but in a different category, the category of differentiable functions. And that's how you get the computable differentiable version of the function. Okay, good. Thanks for asking that question, because I hadn't said that clearly, and that's really important. That's the link between the homomorphism or the functorness here and the conversion of recipes.
Okay. Thank you. Sorry for interrupting again. We have another question. So
Great.
maybe can
Perfect.
you explain once again what's the connection with the old chain rule? I suppose this composition property.
Let's see. What is the connection with the old chain rule?
Mm-hmm.
Okay, so let's go back. Okay, so here's the old chain rule. Okay, so the old chain rule says, wow, the derivative of composition is something to do with composition of derivatives. So sequential composition is probably a fairly nice way to talk about. Okay, and the parallel that has an even nicer property with respect to differentiation. This is probably a good vocabulary. And these linear operations have very nice properties. Okay, but the chain rule is a little bit awkward, which is the chain rule is not strictly compositional. You can't get the derivative of G compose F strictly out of the derivative of G and derivative F. You also need a little bit from F itself. Okay, so the chain rule tells us, it shows us, oops, this kind of this simplest possible thing we might try of just computing derivatives compositionally isn't quite going to work, but it also tells us how to fix the problem. So we needed F, then we'll keep F. Okay. If that's still not clear to somebody, ask again, maybe in a little different way, because I think this is pretty important. I mean, this really is how I came up with this algorithm, is thinking about it in these terms. I knew compositionality is the most important thing in solving any problem. No, defining it is. Secondly, compositionality is. Okay. And then of course, like, try the simplest possible thing. Like, and Buckminster Fuller said, dare to be naive, right? Try the simplest possible thing. And then if it fails, use the failure to get a clue for what's the next simplest possible thing, okay? And so the failure here of strict compositionality says, oh, we need a little bit about the function itself. Okay, so let's keep the function and then see if that's compositional. It is. That's great.
Nice. Yeah, some people are saying that this is a bit like in differential geometry when one takes the tangent bundle and not just tangent spaces.
Exactly.
And we have another question.
Good.
Is recipe a precise notion, or what do you mean by that?
Recipes, no, definitely. It's an informal notion. Recipe is, well, okay, yeah, you can make it formal. A recipe is something for which there is a function, which I wrote here in square brackets. Okay. So what makes it a recipe is that there's a function, square brackets, which I call denotation. I think it's a denotation function that maps it into functions, into something mathematical. Okay. So anything for which you can say there's a way to map it into precise meanings, you can call a recipe. Okay. So programs are a recipe. Graph structures are a recipe. Parallel programs, functional programs are recipes because they all have denotation functions. That's the sense in which I mean recipe. Okay. So the language of categories is a recipe if we have an interpretation of the basic building blocks, identity, composition, projections, fork, and so on. Okay.
I see. Thanks. There's no
Mhm.
more questions for now.
Okay, cool. All right, so here's the game. So the specification of d hat is this. Okay, that's the definition of d hat. It's not computable. But now, if d hat is a Cartesian functor, in other words, if we can come up with definitions of these 5 operations on the right-hand sides of the equations, okay, that make that make these 5 equations true, where d hat is already defined. We don't get to choose d hat. We only get to choose the operations on the right. Okay, if we can solve these equations, then those solutions will be a category. It'll be the definitions of identity, compose, and so on for that category. Then we're going to use those definitions to reinterpret a categorical recipe for a computable function into a computable recipe for its derivative, for a differentiable version. Okay. All right. So solving those 5 equations gives this code. This code is the solution. Now, this was very easy to solve. Why? Because differentiation is compositional nicely in this vocabulary. It's because exactly of the chain rule, the fork rule, and the linear rule. Okay, so if you look here, we have, I've defined this little helper function, linear d. If f is linear, right, then this is the kind of computable differentiable version of f, which is you sample it at a. So it's saying lambda a, that means it's an anonymous function. It takes an argument we're calling a, and it gives you f of a for the value. And what's the value of the derivative at a? It's f, because it's linear. Okay, so the identity is linear, so that's easy. The chain rule is embodied in this line. And so the chain rule, you see, here's where the derivatives get composed. Okay, here's where f gets sampled, and you get a value b and a derivative. Here's where g gets sampled at the value that came out of f, okay, b, and you get c and another derivative. And here we are composing, multiplying, so to speak, but really composing the derivatives and returning the composite value. Okay. All right. Addition and negation. So in addition to having kind of the basic, 5 operations of a Cartesian category, we also want to have some other things like numbers. So addition, multiplication, sine, cosines, things like that. Okay. So negation and addition are linear. So those are very easy. Multiplication, well, we have the Leibniz rule that says the derivative of a product, let's say what derivative of a times b is b times dA plus a times dB. Okay, what does that mean? Well, so this is the derivative part. So a function, so the multiplication is a function that takes a pair, a and b, right? And it gives you back a linear map. That linear map is a function that takes a delta a and a delta b, multiplies delta a by b and delta b by a. Okay, that's just the Leibniz rule. So it's another fact about derivatives. All right. Now, if you look at this, this solution here, almost nothing here depends on how we represent linear maps. Okay, so I'm treating linear maps here as functions. So, a linear transformation is a function that has the property of being linear. Okay, but almost nothing here really relies on the representation, on like the choice of using functions to represent linear functions. Okay. And typically in linear algebra, you don't represent them with functions. You represent them, say, for instance, with matrices. Or if they're one-dimensional, you represent them with scalar numbers, like 3, meaning multiply by 3. Okay. So all we've really used for each of these operations, like the identity, all we needed to know is that there is an identity that's linear for linear maps. And for composition, the derivative of composition, we just needed to know that linear maps are composable. Okay. So linearity is composition. Linearity is closed under composition. Okay, and similarly for fork and so on. But in this one case, for multiplication, actually, gave a kind of a function definition. So in the other, and everywhere else, I use the kind of a more generic vocabulary that can be reinterpreted in other representations of linear maps. So the first thing is just to kind of notice that we needed almost nothing about linear maps other than that they are a Cartesian category in themselves. Okay. So we can generalize this algorithm an algorithm that is parameterized on the representation of linear maps. This really goes much further than linear maps and therefore further than automatic differentiation, but I'm going to just focus on automatic differentiation here. So we can generalize this notion of derivatives to parameterize it by a representation of derivatives. Okay, and we really didn't have to change the code here at all, just a tiny bit. Okay, because I was using composition in the first place. So as long as composition is defined for linear maps for my representation, and it really is a correct, it correctly denotes composition, like for instance, matrix multiplication does. Okay, and then we can use this other representation, but multiplication is a bit awkward. Okay, so we need a little bit more. So here again is the definition of this is the derivative part of multiplication. Okay. And so I want to re-express this, just do a little bit of kind of, refactoring, people call it in programming, or re-express it in more algebraic terms. So I introduced two new pieces of vocabulary. One is scale. And the idea is if we have a type A, okay, that's multiplicative, we can take A and generate a function from A to A. And all it is multiplication. It's multiplication taking one argument at a time. In functional programming and lambda calculus is called currying. So it's a curried version of multiplication. So scale of U. Multiplication is bilinear, okay, which means if you apply it to one argument, you get a linear function out of it. So multiplication applied to one argument is linear. Okay. And then there's this new operation called join. So if you remember fork, it took two functions with the same domain, okay, and gave you a function to the pair of the codomains. Join is the dual of that. If you take two functions of the same codomain, C, it'll give you a function from pairs of the domain elements to C. Okay, and what is that? Well, F join G applied to a pair, AB, is going to be F of A plus G of B. Okay, so I looked at this operation here and I'm puzzling, how can I re-express this in algebraic terms rather than in terms of lambda calculus? And I want to do that so that I can generalize how those operations are defined for other representations, not functions. And if we introduce these two pieces of vocabulary, scale and join, then we could rewrite mul in terms of multiplication in terms of scale and join. Okay. Now, so here's the new pieces of vocabulary, which is, and it's exactly the language of Cocartesian categories. Now, this is going to look funny, because for a Cocartesian category, you would expect to see a coproduct, not a product. Okay, so automatic differentiation is remember it's about local linear approximations, local affine approximations, but the difference between the function and its kind of value at a point is as a linear function. And in linear algebra, coproducts are products. Okay, so linear algebra is a special categorical setting called byproduct categories. And that's really the kind of general setting of this AD work here, and a lot of other things you can do with linear algebra, which is a setting of byproduct categories. A byproduct category is a category of product that has products and coproducts, so it's a bicartesian, and the products and coproducts coincide or are isomorphic. Okay, so that's why this is a funny definition of Cocartesian, because this is really Cocartesian in a byproduct category. Okay, in which the products and coproducts are the same. So, this notion of a Cocartesian in byproduct categories. Okay, so it's dual in the sense that its Cocartesians are always dual to Cartesian, except here we have the coproduct being the same as the product. So before we had a projection that would take a pair and give you the left or the right, the two projection functions. Here we have an injection that you give it the left or the right, and it'll give you a pair. Okay, and the join operation, likewise, we take two morphisms having the same codomain. We get a morphism that has that codomain, but a product which is the same as the coproduct in these categories. Okay, and then one more notion, which is really very specific. Well, I don't actually know, but I think it was specific to linear algebra, which is the ability to scale. Okay, so this is the new vocabulary. We needed join and scale. The injections came along for the ride, and they'll be useful. And now we can ask about differentiation. So differentiation of this vocabulary. And yes, there's also a nice rule that's like the chain rule and the fork rule for join as well. Okay. All right. So now, as I said, so now we have automatic differentiation in very general terms. Okay, it's a simple algorithm, very general terms, and it works for any correct representation of linear maps. Okay. So linear maps form a biproduct category, Cartesian, co-Cartesian, the products and co-products coincide. And there's nice algebraic laws that relate the two. Okay. So for every correct representation of linear maps, this algorithm is going to be a correct automatic differentiation algorithm. Okay. And why is that important? It's important because the usual choice that people make for representing linear maps does not give you a correct, efficient, elegant algorithm for automatic differentiation. But if you choose a different representation, you do get one. Okay, so here I'm going to kind of go backwards and say this is a representation of linear maps as functions. Okay, so this is kind of where we started. I'm just using this as a departing point. I'm going to find a new type here, which is going to be a category. And that type is functions that are linear. So this is in Haskell. Haskell's type system is not powerful enough to get the constraints of linearity in here. That's why I'm kind of redoing this work in Ogda, dependently typed programming language, so that all the linearity is in there as well. Okay, here you just have to be careful with it. And so now I'm giving the instances, the definitions of what's identity and composition and so on. And they're really just wrappers around function, identity and composition for category and co-Cartesian, for category and Cartesian, but not for co-Cartesian. For co-Cartesian, okay, the way you inject a value into a pair is you just use 0 for the missing value. Okay, so A goes to A0, B goes to 0B. Okay, and what does join do? It does addition. Okay, if you use these definitions of the injections and join, you get the co-Cartesian. Co-Cartesian laws hold. Okay, and therefore it's a unique solution. And how does scalar work? Well, scalar works just by partially applying multiplication. Okay, so an algorithm that is kind of assumed functions were what we use to represent linear maps. Okay, and then generalized it and then respecialized it to the old representation, the kind of naive one. Okay, this representation works. It's fine. It's efficient until you try to use information at the result. Okay, so the differentiation is all efficient, but when you're doing high dimensional optimization, we typically want to get a vector out, a gradient vector out, and that the conversion from the function representation to that gradient vector is extremely expensive. It's maybe roughly like quadratic in the dimension, and the dimension might be 1 billion. Okay, so that's why this representation is impractical for high dimensional optimization. Some other applications of automatic differentiation, it's fine, but for the most useful ones, it's like nowhere near being fine. Okay. All right. So I can see I'm running low on time. So
we have a question.
Yeah, go.
So in the instance of co-Cartesian, where these 0 and plus come from?
Where do they come from?
You need A, B, and C to be monoids? Like to?
Yes, yes, exactly.
Okay, I think that's just answered the question.
Yep, that's what it is, yeah.
Thank you.
Okay, so representation by functions is very convenient. It works, but it's impractical for doing high dimensional optimization for that application of automatic differentiation. So what people often do is they use matrices instead. Okay, so we can use matrices as another representation of linear maps. We can get a set of equations, which are we play this functor game. Okay, so the denotation of a matrix as a function that's linear. We can set up the 5 equations for the functorial equations, and we can solve those equations, and you get matrix multiplication as part of what pops out of those algebra problems. Okay, but that's a kind of a decent solution. But the performance of matrix multiplication is highly sensitive to associativity. Okay, so denotationally, of course, matrix multiplication is associative. It has to be, otherwise it wouldn't be a correct implementation of function composition. Okay, but operationally, in terms of performance, it's highly sensitive. Okay, So, so the idea of what's called forward and reverse automatic differentiation is this. The essential idea is that if you use matrices and you make all your compositions right associated, that's what forward mode automatic differentiation is. If you make them all left associated, that's what reverse mode automatic differentiation is. And for the context of high dimensional optimization, you want them all left associated. Then that's why people use reverse mode automatic differentiation. It's much, much more efficient. Okay. So then there's a question of how can we get left association? Because the formulation, right, the recipe, the algebraic categorical recipe is going to be associated however it's associated. There are other reasons like, programming convenience, modularity, that sort of thing that's going to dictate how the compositions come in. But for performance, we want them all left associated. There's a trick, a standard trick, which I think Cayley invented, and Yoneda vastly generalized and was used is still used in programming language called continuation passing form. These are all variants, which is we represent say a function from A to B by a function that takes a consumer of B's and gives you a consumer of A's. That's the continuation form of it, okay? And the mapping is just this. Given a function f prime, I call it prime to be suggestive of derivatives, it's going to give you a function that takes h, okay, that's the B consumer, which you can call continuation, and it applies h after f prime. So that's the specification, okay? Here's it is wrapped up as a category, and this is just the specification right there. And now we want to say that this function cont has to be a Cartesian functor. Okay, so again, that's all we do. Just set up the kind of natural definitions and require that they be Cartesian functors. If we solve these equations with the help of this kind of isomorphisms, we get this code. This is a correct, fairly efficient, I'd say quite efficient implementation of reverse mode automatic differentiation. Okay, it's correct by construction, meaning I just solved those equations and got this code. There's a paper you can look at that has the details, the full proofs. Okay. And so here is an efficient reverse mode automatic differentiation. It's the general the general category D that encapsulates the automatic differentiation as a category, parameterized by representation of linear maps. And that representation of linear maps is matrices. S is the scalar. Okay. R is going to be like the final result type of the function, the final meaning after you've composed all the pieces, what the final type is R that it results in. Okay, so we apply this generic continuation or Cayley or Yoneda transformation, the Yoneda embedding, to that representation, and that is correct efficient reverse mode AD. Okay. And usually this is a very complex algorithm and it's not presented in its full complexity. In other words, it's not presented rigorously. So I think that this is quite a big advance. And now I want to do one more, and I'm going to have to do this pretty quickly because I think we're running low on time. Do we have, Paolo, I'm going to ask, we have to the end of the hour, is that right? Or do we have till 50 minutes?
Let's say the end of the hour also, because you have taken some questions
Absolutely.
in the middle of the talk. So
yeah, okay, cool. And hopefully this will inspire some more questions. So there's one more step, which is really lovely. And it's for the special case in which the final result is after you compose all the pieces is a scalar, okay? So it's one-dimensional. And that is the case for higher dimensional optimization, or for optimization period. So you have an objective function, that objective function is one-dimensional. So, so there's a property of linear algebra, which is called duality, okay? And that's the following, that if you have a vector space U, okay, over scalars of type S, if you look at the linear maps from U to S, okay, those are called linear functionals. I think they're also called covectors or dual vectors. So it's if you look at the linear maps from a space to its own scalar field, then if U is finite dimensional, then those maps are isomorphic to U itself. Okay. And that's why you can think of like a row vector as a linear transformation from vectors to scalars, right? Or if you think about dot products, right? Dot products takes two vectors of the same shape, same dimension, right? And gives you like the sum of the products, right? So if you curry it, you take it apart, and you say dot product applied to one operation, one vector, gives you a function from another vector to a scalar. Okay, that is the isomorphism here I'm talking about. So if you have a vector space U over scalars of type S, then linear maps from U to S is isomorphic to U if U is finite dimensional. Okay, so now we're going to use this fact. We want to represent linear maps from A to B, all right? Well, we can represent them, as I showed you before, the kind of continuation trick by in the continuation form, which is a linear map from B to scalars, okay, to a linear map from A to scalars. So this is just a special case of what I just did, where the return type R is the scalar field itself. So we can represent linear maps from A to B by functions that happen to be linear from B to S to A to S, okay? But when S is a scalar, we can represent those functions from the linear function from B to S by B and linear function from A to S by A itself. And so we can represent linear maps from A to B by functions from B to A, okay? This is what backpropagation is doing, despite all the kind of complexity and state and graph stuff. It's mapping. It's described as mapping kind of errors in B to errors in A. So it says if I miss my result by an amount B, that's the error in the result. How can I tweak my argument so that I get closer to B the next time? That's happening here. Now, just like when we use regular old function from A to B, I said to convert those functions into a vector is going to be proportional to something like quadratic in the dimension of A. And A is typically something like between 1 million and 1 billion. Okay, so that's disastrous for it to be quadratic in that number. But when we represent the linear maps in exactly the other way, as function from B to A, now B, remember, is one-dimensional. Okay, so the complexity is going to be more like 1 squared. It's really going to be more like A itself. Okay. So this is what gets us down from quadratic in a huge number to linear in a huge number when compared to the first approach, okay? And so how do we make this intuition formal? Exactly the way we've done all the rest. We define a new type dual, okay, which we're gonna define as a category, and we'll relate it to something we already know, which is the continuation form, okay, by this formula here. This is all in the paper. You can read for details. Okay, and this dot and dot inverse are the isomorphism I talked about that relates vectors to linear functionals. Okay, and now I want to say that this guy dual is a Cocartesian, is actually a biproduct category. Okay, and so the specification is, as always, as dual is a Cartesian functor. 5 equations. You solve those 5 equations, and you get this code. Okay, these definitions. So these definitions are the solutions of the 5 standard equations for this specification, as dual being a Cartesian functor. And so this is the very efficient, very simple, correct by construction backpropagation or a gradient computation. And if you look at it, you'll see all it does is identity goes to identity, compositions get flipped. Okay, so it's the dual composition of the opposite category. The projections and injections trade places. Okay, so you see the projections become injections, injections become projections, fork becomes join, join becomes fork, and scale becomes itself. Okay, scale becoming itself is like saying, and a way to think about this definition in terms of kind of conventional linear algebra is this is matrix transposition. So I think of it the other way. Matrix transposition is duality. That's what matrix transposition is about. That's why we transpose matrices, because they correctly implement this duality, this categorical duality. And so the scale going to scale is just saying you have a 1 by 1 and you transpose it, you get the same 1 by 1. But otherwise, these operations kind of recursively transpose a matrix, if you think of it that way.
Okay. Sorry, I have a question. So where does dot come from? Are we in a Hilbert space or?
Yeah. So dot is if you're in a finite dimensional vector space, then you have an isomorphism between vectors and linear functionals. Okay. Dot is that isomorphism. Dot is half of it. Dot inverse is the other half of it.
So it's a chosen isomorphism.
Yeah.
Okay.
So this is, this is the punchline. This is the backpropagation algorithm. So this is the entire algorithm. This really is implementation. I use this implementation, which is which is you take the generic simple algorithm for automatic differentiation, and you where the representation of linear maps is the original completely naive representation using functions but dualized. Okay. So this is the final kind of simple, correct, efficient implementation. All right, and I think that's probably a good place to take additional questions. I have some pictorial examples and that sort of thing, but I think questions would probably be more valuable. Are there more questions?
Okay, thanks a lot.
Mm-hmm.
Let's see. Are there any more questions?
Yeah, I want to emphasize that, I mean, there really are some key ingredients here that make this work. One is having a simple, precise denotation, a denotational definition, I mean, a mathematical specification. I think the other is looking for a language in which that problem, the actual problem differentiation, is compositional. Okay. And again, and the what is the properties of differentiation, particularly the chain rule, is a super important clue. The way that differential calculus is often taught in terms of representations of linear maps rather than linear maps themselves obscures that fact. But if you know that the real truth of it is linear maps, then you can see that the chain rule says that the derivative of composition is the composition of the derivatives, not the product of the derivatives. Yeah. And these are the kind of clues to look for. And then this recipe that I use is something I call denotational design, which is look for the specification, look for a language in which to talk about it, and a language in which the problem I'm solving is homomorphic. And so then software design really is kind of formation of tasteful algebra problems, and implementation is the correct solution of those algebra problems. So that's and if you kind of look at my papers, you'll kind of see this recipe over and over. So there's a paper called The Simple Essence of Automatic Differentiation. You can find on my website, conal.net.
Yeah. Do you have a direct link that we can maybe put in the chat?
Yeah, let's see. Oh, yes. Yeah, let's see. Get to the chat. Chat, there we go.
I think I found it. Yeah,
okay.
Let me put it.
Yeah, conal.net papers. And, oh, great. Yeah, good. Yeah, so that archive, that's a good version of it.
So put it on YouTube.
Yeah, if you go to my page, conal.net/papers, and you look for that paper, you'll see some other links with other talks and yeah, some related work.
So let me put that too. So in the meantime, okay, a comment, I guess. It's interesting that this way of looking at derivatives, the one that you mentioned to be obscured by the usual calculus, is actually the way that people usually do differentiation in differential geometry.
Yeah.
Kind of interesting that the approach from differential geometry is the one that's of use here. It's really fascinating. Okay, so we have a couple questions. So first of all, above, which has already been partly answered by the audience, why is differentiation of computable functions non-computable?
Well, why questions, I think, in general are a little difficult to approach. I think the only answer I can give you is look at the paper and you'll see a couple of references with proofs to the non-computability. It's like not at all obvious to me. I think it's a quite deep result. So I don't think I can give you an answer any better than pointing you to references.
Okay. Then we have a question.
I mean, there's an irony here. There's a bit of an irony, which is that integration of computable functions is computable. Exact integration of computable functions is computable. Exact differentiation is not computable. Symbolically, exactly the opposite is true. Symbolically, a differentiation is easy and integration is hard.
That is interesting.
Question?
Also, usually integrals of functions are nicer and derivatives of functions are not as nice in math. That's maybe related. Okay, so we have a question on YouTube from Valeria Paiva.
Great.
That says, I don't understand what's meant by generalized to derivative categories. Can you talk about it? Or what do you mean?
I don't think I talked about derivative categories. I think other people have talked about derivative categories. So I could tell you what I would mean if I did talk about it, which is that this I use very little about linear maps and very little about differentiation. So I use these three properties of differentiation: the chain rule, the fork rule, and the linear rule. Okay. And I use the fact that linear maps form a byproduct category. So I think that this development I showed you works in that setting. Now, any byproduct category and any kind of mathematical operation that has these, these fork, chain, and linear rules. And that includes things like, I don't know all that includes, but one example I think is what's called incremental computation. Which is if you take say maybe a quite complex calculation and then you perform it, it's very expensive, and then you tweak the inputs by a small amount. It'd be nice to do a little bit of additional work. That's a kind of derivative-ish thing, but it's discrete and not continuous. I think that's one example, but I bet there are a lot of other examples. So you might take those properties, those collection of things that were used byproduct plus these few rules, and call that a derivative category. But I don't know if that's what people mean by derivative categories in the literature.
Okay, she says, that's good. But she's asking, infinite dimensional vector spaces are out?
I do not know. Well, no, they're not. No, they're not out. So I use the isomorphism that depends on the finite dimensionality just at the very last step for doing this kind of what I call backpropagation. But if you back the algorithm, if you back up to the previous version, and I just use the kind of Cayley continuation Yoneda trick, I think that works fine for infinite dimensional. It was really just the punning of linear functionals with vectors, and I don't think that's a particularly important step.
I see. So we have a question by Paul Taylor. You should be unmuted. Feel free to ask.
Well, let me start with a compliment that it's a very nice fusion of category theory and functional programming and numerical computation, to the extent that I can't tell from which discipline you come.
Well, thank you. That was a nice compliment.
So okay, so I'm still confused about the transformation of the chain rule, but I reckon I can probably work that out for myself after the seminar. So I'm a categorist, by the way, in case you don't recognize me. So let me ask a question from the point of view of numerical computation. So the crude way of doing this kind of thing will be a massive transformation of trees, and I guess there's most UN in the trees and so on. If you apply your algorithms, how does that correspond on the trees? And I mean, I guess the numerical people must have tricks for reducing the duplication. How do you perform in comparison to them?
Okay, I'm not sure I understood that. There was a little audio issue. Are you saying with trees?
So there's a symbolic differentiation.
Yes.
If you've got your expression represented as a tree, and then you do that, there's going to be some massive duplication of the tree.
Gotcha.
Okay. Yeah, that kind of thing. I think.
Thank you.
So how do you have an algorithm that gets rid of that duplication, and how does that compare with what the numerical people would do?
Yeah, thanks. Okay. So I think if you mute yourself, we'll get rid of this echo. Hello. There. Yeah. Okay. Thank you. Perfect. All right. So so the literature of automatic differentiation talks about, typically say that there's three ways to approach differentiation on a computer. One is numeric approximation, which that's not even, because that's not correct. All right, so there's that approach. And then there are these other two, which are called symbolic and automatic differentiation. And the AD literature says, well, of course, automatic differentiation is a good one. Symbolic differentiation has a few problems, and one of them is code duplication. Okay, so if you like symbolic differentiation, it's very easy to like blow up and get possibly exponential, but at least very large kind of blow up and duplication of work. Avoiding that work is very challenging to do efficiently and rigorously. Okay, it's usually done statefully, which makes it hard to do rigorously, or it's done rigorously, which makes it hard to do statefully. Right, it makes it hard to do efficiently. All right, but I don't agree with this perspective. I think I think the problem, the efficiency problem that you're bringing up, Paul, with duplication is about doing differentiation badly. If you do differentiation badly, meaning specifically if you don't take care around sharing or around reuse, then you're going to get this issue. Okay, but that's not really about symbolic differentiation. That's about symbolic differentiation without the ability to address sharing, without the ability to represent sharing. You need some kind of construct like a let, or do like a DAG, a directed acyclic graph instead of a tree. Okay, so I think for me the difference between symbolic and automatic differentiation is just this. Automatic differentiation is symbolic differentiation when it's done by a compiler. So automatic differentiation to me is doing symbolic differentiation, but taking advantage of a compiler to help. Okay, so compilers already work symbolically. Everything they do is symbolic. And compilers are good at tracking sharing and watching out for not redoing computation. That's what they do. So it's actually really easy to avoid the sharing blow up problem when you're inside the compiler. Now in the categorical setting, it's extremely easy to do it. The categorical setting is ideal because Cartesian categories have an operation which is duplication. Okay, so there are different ways. If I'd factored the Cartesian differently via a monoidal category that introduces the tensor and then a Cartesian on top of that, I would have added first and second projection and duplication, and that's really how I do it. The duplication operation itself that encapsulates exactly this kind of blow up danger, but it encapsulates it in such a simple way that it's really, really easy to avoid the blow up. Specifically, the duplication itself has a derivative. Okay, so the derivative of duplication is duplication because it's linear. Okay, now in the dualized, in either the continuation or the kind of pure dual version, the dual of duplication is addition. Okay, and the dual of addition is duplication. And if you think about it in terms of like a row and a column, one of those is a row vector 1, 1, and the other is a column vector 1, 1. But really abstractly, addition and duplication are exactly duals to each other. And so when you do automatic differentiation in this setting, using these duals, what happens is every time you have sharing, the sharing is, I forgot to say this, okay. So the way that you use this, everything I talked about here in the setting of like a real programming is, a nice thing about the categorical language, not only does it make differentiation compositional, but you can take an arbitrary functional program, an arbitrary computation, lambda calculus expression, and translate it into the language of categories. That's what really makes this a practical tool, that setting. And when you do that, whenever there is duplication in lambda calculus, that's going to look like a lambda, okay, or in sugar version, it'll look like a let. And the translation is going to introduce a dupe. And when you go and differentiate that dupe, it'll just become a dupe. Or if you do this dual version, it'll become an addition. Okay. And that's why there are additions in derivatives. Okay. It's because that dupe turns into an addition. So it's really easy to do this very efficiently and very elegantly. So I hope I answered the question that you were asking, Paul. And if not, I hope you will reach out to me and ask it again.
Okay, we have a comment which I think is related. Gershon Bean YouTube says, if you plug in a symbolic tree instead of numbers in your category instant, you do get symbolic differentiation out. So you can recover it in this way.
Yeah, and you'll get the bad version that we were just talking about, the one that's because you use trees. You can't use trees at a representation and get efficient sharing. So yes, you can, and you don't need to, because you already have symbolic differentiation done much better than what you just described, because that's what a compiler does. You put this inside the compiler. So for me, so these categories get put into the middle of a Haskell compiler via a simple little plugin that I call compiling to categories. You write a Haskell program, then you specify, I don't want the usual category of computable functions, I want some other category. And that category's got to be Cartesian. And if it's closed Cartesian, that's really convenient. And when you do that for automatic differentiation, it turns Haskell programs into differentiable Haskell programs. Okay. And so, yes, there is symbolic stuff going on, but it's done better than you would do it yourself because it's done by the compiler and you don't get blow up.
Okay. I feel Jax may want to say something about it. Then there's some other comments about other questions which I'll address after this.
Yeah, just one comment a little bit on the inefficiency of symbolic differentiation and why it remained like that for a long time, since it's so obvious how to fix it. Part of the problem is the language of algebra.
Yep.
As a first order language does not contain let in.
Exactly.
So
it's so easy to fix.
Because the output would be jarring in algebra to have a let, you can't express sharing when you're doing symbolic computation, and therefore you get the wrong answer, which is too big, and you get it right in the context of a programming language because, oh, let is now free, whether you call it equal or whatever, and it's merely the shift of language, of allowing let in your language removes an exponential inefficiency.
Yeah, and it removes it from everything, not just from differentiation.
Yes.
Yeah. Yeah, so it's not a differentiation issue. It's an issue of not having the ability to express sharing.
Right.
And category theory has a different way to express sharing than lambda calculus. And it's actually much nicer for doing analysis. Thanks, Jacques.
Thank you to both. Okay, so JS, I guess it's JS Lemay, had a comment. You are unmuted if you want.
Yeah, hi. I guess
Hi.
I do these things called differential categories. And so I just thought I'd mention that people have started looking at automatic differentiation in these differential categories. So maybe differential categories and Cartesian differential categories and tangent categories and all that differential category stuff might be interesting to you. But specifically what people have done automatic differentiation in differential categories, I think Gordon Plotkin is probably better suited to answer that question or to comment further on that. But I just thought I'd make the comment that maybe you'd be interested in that stuff.
Cool, thanks. Paolo, you're muted.
Thank you, sorry. We have a question by Pat O'Neill, who's unmuted if...
Sure. Thanks very much for an interesting talk. I have a very naive question, which is that often in AD, you encounter dual numbers, right? So you have a field where you take the reals and you join this element epsilon, such that epsilon squared is equal to 0. And then you just proceed as usual, and you stuff these dual numbers into your functions, and then you pull out the dual component at the end, and you have the derivative sort of for free or almost for free. And this allows you to take the derivatives of things you would never expect to be able to take derivatives of. I was just curious, like, is there an interpretation of this method in this approach? Like, does it clarify where these things come from?
Yep. Yeah. Thank you. Yeah. Right. Yeah. So that's a common approach to these dual numbers, and I think it only works for scalars, for one-dimensional differentiation. Yeah. So dual numbers are where you pack up a value and a derivative, and you can manipulate those at once. I think that there's a deep bug in this idea of dual numbers, and I'm sorry that people are enchanted with them, which is that most functions from dual numbers to dual numbers cannot have to do with different derivatives, and that's because if you have a function from a value and a derivative, right, to a function to a value and a derivative, it suggests that both the value and the derivative coming out can both depend on both the value and the derivative coming in, and that's not true. The value coming out cannot depend on the derivative going in. The derivative going out depends on both the derivative coming in and the value, but the value going out cannot depend on the derivative. If it were, it wouldn't represent what it's trying to represent. So you can take that idea of a value and derivative function to a value and a derivative. You can say, oops, there's a little bug here, which there is. The value coming out cannot depend on the derivative going in. Okay, so then you say, all right, we're gonna shift it up a bit. We're gonna like first curry it. Say we're gonna take a value going in, and we're gonna give you a value going out and a function from the derivative going in to the derivative going out. That, and by the way, that function is linear. That is the general notion of that I call these differentiable computable functions. Okay, so let's remember, because I had a going in, and what comes out is a b that doesn't depend on derivative. It doesn't depend on delta a, and a linear function from delta a to delta b. That's a correction of the what overly lacks dependencies that the dual numbers suggest. Moreover, it works for arbitrary dimensions. Yeah, so there's something that seems to be a little appealing about this dual number trick. But I think it's just one of these things that almost kind of works if you don't look at it too closely for a small special case, and if you're careful how you use it. So I don't know, I might have offended a bunch of people. I hope not. But thanks for the question, Pat.
So we have Jacques and JS. Do you have any further comments? You should be free to unmute yourself now, seems no. Oh, okay, but
I really appreciate all the questions. I'm glad we had time for them.
Yeah, many people are thanking you also on YouTube.
Oh, cool.
And okay.
All right. Well, and if anybody has anything else come up, feel free to email me. I always enjoy corresponding with people.
I see. Okay. Anybody else has any questions or comments before we go offline? No, people mostly want to thank you. And okay, I want to thank you too. Thanks a lot for your talks. It was very nice.
All right. It was a pleasure. Yeah, thanks a lot for having me.
It was really nice to see category theory coming up with such a useful thing. Doing its usual job of saying that something is actually obvious.
Yeah.
Of course, once one understands it.
Yeah, tremendously useful.
Yeah, it was very nice, very nice. And okay, so let me stop the streaming, and yeah, please see you next week. And thanks.
Okay.
Again.
Yeah. Bye bye. Take care.